Hello, everyone. My name is Rafi, Manager Rafi. It is a great pleasure to give you this talk today. The title of the presentation is The Rise of Machines and VCM Standards, with an emphasis on video transformers. On the outline, I start with giving you a very brief introduction on Gyrfalcon technology. And the reason for doing this is mostly to give you some background from industry perspective on the need for video coding for machine and show how this standard can drive industry. Which brings me to the next topic, which is the emerging MPEG VCM standard activities in our ad hoc group. Under that, there are a number of use cases for VCM, including smart cities, smart transportation, smart industry, intelligent content, and some more that are under exploration in MPEG VCM ad hoc group activities. However, I would like to mention two key real-world applications of VCM, specifically in automotive and AI-powered cameras, which are among the biggest growing market segment right now. Then I get into the core portion of the talk that is on the new field of transformers, specifically in vision computing. As you know, this area is well established in NLP. And then I get into discussion of some of the analogy and differences between convolutional networks and transformers, specifically including attention mechanism. And then I talk about the technology trends and some challenges. Then I conclude with some future prospects. The headquarters is in Silicon Valley. We have 2 branches in China, 2 in Japan, and 1 in Korea. The company has founded in 2017, and since then we have 4 chips in production. Also, we do have an ecosystem of chips in terms of boards, a system, and of course, a software chain tools. GTI has over 90 patents filed, and over 50 of them have already been awarded. We have received also a number of awards and recognition in the last 4 years. And as you can see, GTI is very well versed in the media. Just want to give you a very brief background on the architecture, specifically for AI and deep learning, on the chip architecture for machine learning and deep learning. Again, it was traditionally started by using available hardware resources at the time, being CPU or DSP. However, DSPs and CPU are general purpose processors that often used for various complicated tasks. And the processing are like more on pre or post signal processing, housekeeping, and often they have a scalar type architecture. On the other hand, we have GPUs, again, led by NVIDIA, which have been used, again, traditionally for gaming and graphic processing. The architecture is often one-dimensional vector, but very powerful and flexible. However, it is somewhat expensive and not very power efficient for all application that is used for AI. They are mostly used for training and for application, or mostly in data centers and cloud, because of it is very it's not very cost effective. On the other hand, we have the architecture for deep learning, which is distributed basically tensor or matrix processing with distributed max and memories that are in proximity of the engine itself. So all the AI processing is done inside the memory, inside the chip, including the data flow control and ALUs. This way, you don't have to go in and out of the chip, because you know that if you go in and out of the chip, you kind of consume lots of power, and over 70% of the power consumption is just coming from the I/O processing. The chips that we have on the performance side, depending on which chip you're choosing, is from 9 to 24 TOPS per watt, and the power consumption is sub-watt, under 1 watt for all of them. Here is a little bit of background of the chips we have. I'm not going to go through each one of them. Just want to emphasize on the efficiency of all the chips, as well as the power consumptions, as I mentioned, is under 1 watt. Now, on the video coding for machine itself, the emphasis is on two technologies for machine, being feature extraction for shared backbone and feature compression with some gains exceeding that of VVC. That's what we're trying to address in the committee. For that one, there is a latest MPEG roadmap and all the emerging standard activities in the area of either media coding in terms of the systems and tools, as well as beyond media. VCM is one of the active ad hoc group with over 450 members from a very diverse and respective groups of industries, universities, and other research institutes that have been significantly contributing to VCM activities. I highly encourage you and invite you who are interested in this space, participate in MPEG VCM activities. At MPEG, CDVS and CDVA, which is compact descriptor for visual search and video analysis, those are already established as a standard a while back. And in each one of them, for example, on CDVA, all of them are feature extraction. On CDVA is more on the local and pixel level feature extraction. It was more man-made or handcrafted. On CDVA, it was more on the global side, on the picture level. It was the AI driven. And there are so many contributions since then, like Super CDVA. Again, this is the caption CDVA, tile CDVA, BERT CDVA, etc. The one that we are focusing right now is VCM, video coding for machine. And that one is overall very generic, local, as well as global AI-driven activities, both on the feature extraction as well as compression. There are a number of great contributions so far we have received, mostly on encoding, machine task outputs, encoding intermediate feature maps, learning-based imaging compression, and there are some also based on the traditional video coding technologies like VVC, some modification of those areas. On the automotive side, as you know, that we need a very powerful engine, a computing basically engine to make the AI processing happen, because there are so many activities going on in the autonomous driving. Then, of course, we have some other standards called 5G for connectivity of the cars or intelligent connectivity. And we believe that the video coding for machine, or CDM, can play a significant role in this space. As an example, if you look at a car with a bunch of cameras surrounding the car, and the car is looking out into seeing basically different events or activities, traffic, pedestrian, objects, etc. The cameras capture these events and bring inside, and they may want to process that internally inside the box, inside the car. Or sometimes you want to send this information to the surrounding environment, being other cars, or it can be on the side road, for example, a cell phone or a cell tower. And then you may want to broadcast that one into the macro and macro cell, and then broadcast that to the whole grid. Let's say there is some accident, for example, is happening, and you want to go all the way and send it to a region. And sometimes when you do the analysis, you don't want to send your own analysis. This is your own activities. You can only send basically the features or the compressed features to other cars, and they want to do something differently, some different task even in there, or they do not want to use the algorithm, or they don't rely on the algorithm used by other vendors. So that's going to be very helpful to have some standard to be able the whole community, especially on autonomous driving, to share with the help of 5G and V2X. So VCM can be some kind of communication language for machine to machine and machine to human activities. Similarly, on the camera side, as you are very familiar, the smart cameras, they have a bunch of cameras. And then there is the ISP, which does lots of functions in there, predominantly for denoising, demosaicing, HDR, some enhancement on the video, and super resolution, etc. The idea is why not, we go inside the cameras, actually some of them are already using, and put the AI processor and pair it with either ISP and other processor you have, and be able to either generate some analysis, being face detection, authentication, etc., or it can be some enhancement or super resolution for human consumption. Ideally, at some point, we would like to have an end-to-end AI processing inside the camera, that is having a single chip replacing ISP, and then be able to do both, for machine consumption and human consumption in there. That's what the different activities are going on right now in real world. For example, on automotive, there is some activity in terms of the direction, which direction automatically we are going, and give you it is a go forward or backward, etc. It can be for any robotics. It is the semantic segmentation or instant segmentation that you can see there, and the line changing, for example, on the cameras or on the automotive activities. This one is very interesting. This traffic light detection, when the traffic light normally is very small, and for very small object detection, and when you have the very high resolution camera that is very effective, you may want to understand the behavior of the video, what is happening, or some gesture also that shows that what kind of gesture a person is doing. It may be some emotion, for example, some object detection, and a super resolution and other things that can be happening inside the AI. Now, the question is, how can we do all of them in there? We get into the main topic of the important topic of discussion, which is transformers, or rather video transformers. We have seen that the CNN or convolutional networks have been quite effective and successful with very impressive performance, and have dominated the space in visual computing for many years, particularly in image and video fields. Now, the big question is that we're going to ask through this discussion is that, and the researcher also is asking right now, is whether transformers, as you see it in a minute, are a viable alternative for convolutional networks or not. So what we're trying to say or trying to ask is that, can transformers be considered as the next gen for deep learning or neural network applications? If so, what are the impacts or direction of these on standards, on industry? Can we really claim what some people say, transformer is all you need? Is that a true statement? Or maybe we can say convolutional network is not all you need. That is, we need something beyond convolutional network in our analysis. Before that, give you a very quick background on the transformer evolution and this height growth, specifically in computer vision. As you know that this transformer started not in 2017, it's really started kind of in 2014 or so. But the transformer models established more recently with a great performance on a broad range of NLP and language tasks. For example, text classification, machine translation, question answering, etc. So there are attention-based models that started with a well-known paper, which is called Attention is All You Need. That one was in 2017. It was a Google researcher teams. They offered a very generic and very robust architecture that has become a very classical pipeline for other transformer-related tasks since then. Then building on that, in 2018, again, we have something which is very most popular transformer. It is called BERT. It is bidirectional encoder representation from transporter, with a very impressive state-of-the-art performance on NLP field. Then, of course, in 2019, we have a so-called robustly optimizer, again, built on the previous one for BERT with pre-training, and then T5, which is standing for text-to-text transfer transformer. Then you're moving to 2020. As you see, all this publication is happening here. It is a big jump just last year in this area. And that one is more in something called GPT, a generative pre-trained transformer, different versions of 1, 2, or 3, or image GPT, or detection for transformers, or image processing transformer for super resolution, denoising, for example, and other low-level activities for video and for image. Then it is this year, even though we are not through this year, it is tremendous activities, progress on transformers, and we have witnessed amazing transformers architecture for visual processing that are either paired with convolutional neural networks or they are entirely replacing the CNN. For example, on this video transformer, that one, there is no CNN in there. It is purely transformer. And actually, most of them are that way. But sometimes for having a more efficient transformers, as you see later, you may have to pair it with convolutional networks. Now, transformers in visual data, because after we had a great success of transformers in NLP, the next step is on visual data. Transformer already successfully used and applied, again, transformers for recognition tasks, including classification, detection, action recognition, and segmentation. Also in generative modeling and multimodal tasks, like image generation, visual question and answering, visual reasoning. Also for low-level activities like video processing, like activity recognition, super resolution, enhancement, video forecasting, and even on 3D analysis, like point cloud classification and segmentation. And then the trend is to replace convolutional operation fully with attention-based transformers, or to pair convolutional network and transformers through a single design to have a set of complementary operations. These are the two areas that people are working right now. The next thing is, what is really the strength of the transformers? The strength of transformers has been already, as I mentioned, established through amazing results on NLP. That is, in NLP, basically all is used is transformers in there. And that one is on sequence to sequence model. That is because of the dependencies that we have within the sequence in there, being words, or now it is images or image patches or clusters are used in there. Then that enable modeling of long dependencies between input sequences. This is one of the capabilities of transformers. And the attention function allows the transformers architecture to compute in more like a parallelized manner, because these are work on different basically area of your pixel or words or token independently. You're able to use the hardware more effectively this way. Unlike the convolutional networks, transformers requires no inductive biases. Inductive biases with the prior knowledge, or even if they use them, it is very minimal. That is why these models are very generic. And mostly they are very straightforward design that is using a very similar or simple block processing that can be used very often in the whole pipeline. It also allows different multiple modalities, including image, video, text, and speeches. And they have excellent scalability for a very large capacity networks and huge data sets. That is a very different characteristics of these transformers. And they have much more powerful for complex tasks, provided that you have a data to train it. Again, this having data is a big enabler for transformer. Again, one of the reasons that we were using CNN and LSTM and others, or RNN, partially they have inductive biases, partially because we have much smaller data sets. Not right now, we have huge data And then what we are saying that transformers are going to be able to learn all these inductive biases and learn what the CNN and others are doing. So that's why we are saying a transformer-based pre-trained model can achieve a state-of-the-art performance on many tasks. That's why, again, researchers, it is a go-to architecture, not only for NLP, but for computer vision, particularly for these pre-trained models. Again, two things that to mention, one pre-trained models, and the other one is the huge data sets that we have. And the convolutional networks that we are mostly familiar with, either be CNN, LSTM, RNN, etc., as I mentioned, they have some form of prior knowledge. They have some inductive biases. And they are also capable of some equivalency for translation and locality, that they do this at the same time, as you can see on the right side. And they do it by some relatively small filters to compress the information and create that locality and coherency within a limited local region. Convolutional neural networks, they do not, they cannot be considered for a distance pixel relationship. That is, things are done locally, but with going deep into the layers, you try to create that perceptive field that you need eventually, slowly, as you see ResNet and other applications. Convolutional neural network architecture cannot support the parallel processing, as I mentioned, because of those dependencies. It does not allow to simultaneously extract all information from the input and its interrelation compared to transformers. That is, transformers, one of the key area of them is that capability that, again, simultaneously can capture all these different entities from the input side at the same time. Convolutional neural network performs well mostly on a smaller scale data set, while transformers performs much better on larger data sets. So sometimes even when we have a very large, we may have other issues with convolutional networks. Whereas the more data you throw at transformers, the better it gets. So what are the successes in the transformers as well as we've seen it? Basically, the main thing, of course, is this so-called self-attention. Self-attention not to local, but to global dependencies. That is the availability of these big data sets, the largest data sets, and be able to pre-train them with these large data sets and then downstream it to much smaller data set or more specific data sets for some tasks. It also has the bidirectional feature encoding and decoding capabilities. This one also has some challenges with it, all the transformers, being the high training and computational costs. We have seen that in BERT, we have seen it in GPT-3, again, even in the video transformers. And the complexity is mostly coming from this attention function, even though it looks simple, because we are doing it with all pairwise, all different combination, the size of the picture, all the length of the sentence. It is not linear, basically. It is quadratic, exponential, and then that is causing issue. And these efficient transformers are trying to address this area. If they have high memory requirement and parametric complexity, as I mentioned here, they do not necessarily need any inductive biases. Not having inductive biases, they're going to rely more on large amount of data during pre-training. That's why data is very important. While powerful for general purpose tasks like classification or recognition, they do not have spatial information necessary for many other tasks. For example, instance segmentation. Again, these are some of the open areas that researchers are working on it. To address the solution, people are looking for so-called efficient transformer or X-formers. That one is more to address this training time, this big memory requirement that we have. For that, they're looking for things like sparse, metrics for attention, or be more selective, so-called deformable transformers, including, introducing some inductive biases to the model. For example, you see later in transformers, sometimes we want to inject, something like, let's say, residual connection or a skip connection. those are actually, we are changing those generality by inserting some biases. Actually, that's a very strong bias that we're injecting in there. Or sometimes they can use this in efficient transformers. They use a special relationship in local neighborhood. And then sometimes we're not operating on single pixel anymore. We are looking at image patches, for example, a token group of, basically patches or clusters, or we use some windows on them or some shifted windows on them, which is that kind of getting on the macro level of convolutional network that what we are doing with filters. And the other thing you're trying to do is to pair that with convolutional feature to get a better performance. Again, most of this area, the upper portion, is how can we go from the N2 complexity to N or linear N or linear log N activities, that some of the research activities and papers are on those areas. The other one is the efficient data. Even though the data efficient image transformer is already introduced with some distillation approach, and sometimes they use the CNN as a teacher to teach the student so-called vision transformers for them to train, and then after you train them, then they can use on the smaller data sets. The other one, of course, is the hardware. Now, what is the future hardware for transformers? It's going to be GPUs, FPGAs, or it's going to be ASICs that we need for acceleration. Although replacing this convolutional neural net, or by self-attention so-called, is theoretically efficient and possible, it is not yet scaled effectively on the modern hardware accelerator. That is what some of the companies are working on, this specific area. That's one of the interest area to us as well. Again, if you look at the convolutional neural network with a picture or image, as I said, it is more local. However, if you look at the transformers, you're trying to look at not just locally within some filter that we have some kernel that in there. At the same time, you're looking pairwise of each, let's say, area. In this case, let's say it is a patch with all other surrounding patches simultaneously. For example, if it is in Word, in NLP, if you're looking at a sentence, we're trying to find all this correlation that we have, all the similarities that we have between all different token or words, between all these activities. For example, here we have the strongest relationship. And based on that, we come up with some, softmax at the end and try to predict, what is the next image or next word is going to be, as it's used, in even translation language or prediction, etc. It brings it back to the first important paper I mentioned, 2017. Attention is all you need. As I mentioned, it was in 2017, a team of Google, Vasmani, actually in there, officially introduced a self-attention mechanism called Attention is All You Need, a very nice name. And this paper got a great surprise within NLP research community, that the model is using no convolution, no CNN, no recurrence, no LSTM, and yet it is able to outperform the existing sequence-to-sequence neural network machine translation. That is what is used, again, traditionally using, again, LSTM or RNN. This model is composed of a combination of an encoder and decoder, with encoder taking sequences as input and mapping to what is known as n-dimensional vector. The vector is then placed into a decoder and it generates a resulting output. And of course, inside you see that there is some self-attention mechanism, some feed-forward network, and that thing is repeated here, as well as there is some other attention function which relates the input and output. Again, we talked on this more in detail. So again, reliance on CNN is not necessary. This is a big message. Replacing the entire CNN with transformers. Transformers is pre-trained on a large, these are huge data sets. This is 300 million, basically, images that we have. And then we can fine tune it on the smaller size task-specific data set, like ImageNet, etc. and can achieve either the same or even better, exceed the state-of-the-art result compared to existing CNN for this application or LSTM, and attends to every other pixel. That is the issue with it, actually. Issue in terms of it is expensive, in terms of memory, and it is N2 related in terms of complexity. Just to give you a very quick background, the architecture, it is composed of two blocks. The first one is, of course, encoder. It is on the left side. This is the encoder side. And then we have the decoder side. And for the encoder side, it is composed of multiple layers. This N is layers. In this example, they use 6 of them. Same thing for the decoder. They use 6 of them. And then they have the input. The input is the image. It can be the word or whatever it is. Basically, you have to transform that in some way or fashion into some vector, some number, so machine can understand that. And doing that, you use some kind of embedding inside, which is very typical, embedding of input embedding, they call it. And because we are not using any recursive algorithm, which we don't have any notion of the memory, it is also, they do something called positional encoding for sequencing to understand, where everything is. Then after that, we fit them into the encoder in there. Inside the encoder, there are again 2 blocks. One is called multi-head attention. This is the major attention function that we have. And that one also repeated here inside the decoder as well, with some minor modification. And then the feed-forward function. This is just linear feed-forward. It is not like convolutional network that we have the activation of some nonlinearity in there. And then we do some normalization, and we add then, this is the skip connection or residual connection to preserve, basically like, ResNet, to preserve some information as we go deeper and deeper, or we have the multi-layer. And then we normalize it, that is, we try to, for gradient descent and propagation, back propagation, we try to make it, to 0 mean and then a standard deviation of 1. And we do that as every stage going forward. On the decoder side, we have actually 3 sublayers in there, as I mentioned. By the way, what we are providing in the input on any trivial analysis, normally we have some query, some keys, and some values. At the beginning, normally we use all of them either randomly or the same duplicate of each one of them, or they're going to be learned eventually inside this block. And then here, what comes out of this thing is going to be the key and the value. And this one is the already detected output. Let's say you have a sentence and then you have detected, half of the sentence yet, and use that input, use the same process, go through some multi-head attention, and then combine them, with what you have from the encoder and do rest of the process. So what is this multi-head attention that I mentioned here? The multi-head attention in general is composed of this V, that is the value key, and then the query coming in. But in reality, they don't use just one layer. They use a multi of them. In some cases, they use even 16 of them at the same time, so that when you want to do some similarity here, this is a dot product similarity inside this block, we have a different attention, not just one attention. Maybe you want to have attention on the background, certain portion of the background of an image, or only on the image, etc. And use all of them and concatenate them and use some projection on it. And then that is the output coming out of it. But what is this one? This one is a very simple similarity function. It can be a cosine function, for example, a dot product that you do between Q, the query, and then the key, and then you scale it basically later with the V. V is the value. And the complexity of this one is the one which is causing issue, is it N squared. And for that one, similarity, there are many ways of doing the dot product. It is a simple dot product. It can be normalized. It can be weighted. It can be addition of version of that. But the one which is used universally right now for this application is this dot product that is this dot product you're doing here between Q and K, and then you do softmax to get all the probabilities, and then you multiply it by what comes from the value here. This one is the modification of this block just to make sure that the future, which are not available yet from the output, are not included in this calculation. It is a kind of like autoregressive kind of model that you use for this. So that's one thing that is used, again, very successfully, as I mentioned, for NLP. Now, the same group basically came and said that for image, we can do the same thing. That is, they call it an image is worth 16 by 16 word. This also came recently out. It created lots of attention for many people. That is, then you have, it's the same concept, you have your picture. All these pixels, if it is N2 related, it's very difficult to manage it. So what they do, they come and divide that or split that into patches and get these patches, basically vectorize them, convert them into a vector, and each vector may have their own latent, for example, can be 512 or more, whatever, they're going to be choosing there, and then combine them and send them into a linear projection after they are flattened, all the patches, in the linear projection for flattening all the patches so that we have the vectorized representation of the original image. And then you do basically some, as you have seen before, position embedding, because we need to know all the sequences where they are. And sometimes, like a BERT, they have some classifier included in the middle. Then you get all of them and then go through this transformer. Again, transformer is very similar like what they proposed before for NLP. It's almost the same. It's the same actually for the encoder side. And then you do all this processing and come out of it through a multi-layer perception, basically, and then go to classification and other tasks that you need to do. Just give you some experimental results that they have. You notice that this is the model, the VIT, basically what they have. It is the video translator or vision translator. And this 1416 is the patch size, 14 by 14 and 16 by 16. If it is 14 by 14, it means a smaller patch. It means more patches, more number of patches. If it is 16 by 16, it means it is a smaller patch. It is basically a bigger patch, and it is a smaller number of patches that we have. So if you compare these with some of the traditional ResNet or efficient net, look at the performance. You look at them, it is dominantly, even we are not using any CNN, the performance is better. And more importantly, on the cost of the training, you notice that this one is taking quite a bit for big data that we have, 9.9K in terms of this unit, core days. Even this one, which is 14, huge model that they're using, it is smaller than this. Yet if you go to 16, it is a fraction of what you see here. What is very interesting here, look at some of this attention base, what is really happening inside, this transformer. Again, this is the similarity between all the columns and rows that you have through the cosine function. You see, for example, in its corner, you see that this one is more similar in this point, and then in the center is different. These are the filters operation on RGB, basically embedding filters that they have. Very similar to convolutional neural network. It looks like the wavelet here, what you see here. But what I want to emphasize is this unique figure here. What is this one? This is the depth of the network. In this case, they have 24 layers, for example. And here the mean attention distance between pixels. Mean attention distance, that is the pixel to pixel dependencies. How do they measure that? The bigger, it means that like the pixel 100, the distance between this and pixel of 100, they can basically in early layers, they can do attention. They can pay attention to it. This is very, very interesting that what they do, even it is not deep yet, it is earlier stages. Many of these heads, as I mentioned, there are many representations that they have. In this case, they have 16 of them. All these dots can understand and not correlate, can attend to this behavior. As you go beyond, let's say 10, then this kind of global and local doesn't matter. So here it looks like we have a global attention also here, where here it's more local attention that we have. So CNN, it is more on local attention. That is, as you move forward linearly, you go up. For example, if you do CNN, this is the behavior more you see, rather than having this information back here, which is very interesting to see that. The other one is the next step. Even this one that you just saw is the fixed windows. They are saying that why not, we improve that from N2 complexity to N complexity. This one is from Microsoft people. And they say we get these patched images, maybe a smaller even patches. And as we go forward, we scale them, and we also try put them back together in terms of a patch merging, they call it, and then go that way. So it means that it is a general purpose backbone. This is what is on the backbone. They claim it can be a very good backbone for computer vision. It is the hierarchical transformer, and they call it, these are basically a window or shifted window. I show it in a minute. And they're using a self-attention computation on non-overlapping local windows that we have. And they show that they have a very strong performance on COCO object detection, as you see it in a minute. Again, this is from Google, and this is the latest one that they're working on. So what they say that in this pipeline, what they have the image, you partition the image first and do the very simple linear embedding as you have seen it before, and some transformer. Transformer is different because we do some windowing on the first stage. On the next stage, then because you're trying to merge the patch, in that case, all of them, the smaller size that you have for height and also width, you have to compensate that by the output channel. That is the output channel. If you divide it by half, the output channel is going to increase to get the vector right. And you repeat this sequentially, basically, in the go forward. Here, what you have also, you have, as I mentioned, it is very similar to what Google has, except that they have this multi-head self-attention. It is window-based. And this one is a shifted window-based, multi-head self-attention that they have. So what they do when on the shifted window, it is like the kernel of the CNN. They go and then try to go around like a filter that they have. They go around in different windows. Again, these are the different big windows, and try to not only get the global, but get some local information on this model. Again, they're testing that into two data sets. One is a smaller one, ImageNet 1K, the other one 22K. Just notice basically, based on what they have, this is Swin, this basically shifted window that they have for different models, depending on what kind of channel you use and how many layers you use here. And the performance is very comparable even on the small data set. However, we go to a bigger data set, it is significantly better. Even again, we are not using any CNN in this one, and it is basically the visual processing, which convolutional neural network supposed to be the leader in this area. Very interesting. Now, on the conclusion, I just want to say that the transformers are becoming really hot topic in computer vision. It is a shift of paradigm, as you have seen it, and transformer can be considered a generalized or superset of this multi-layer perception. The multi-layer perception is also superset of CNN or LSTM. That is, CNN is a specialized version of MLP, and this transformers are even less a specialized version of MLP. They require massive data sets for large scale training. Again, they don't need any inductive biases here. We can provide that if needed. And the application, you have seen it for computer vision, anything from backbone, the latest one from Microsoft, on anything from high level like object detection, classification, to low level, for example, to resolution enhancement or changing the color, or even to video generation and processing using transformers. Again, no need to introduce any inductive biases, even though it may be helpful in certain cases. And then all it needs is basically data, large data. The images and frames are interpreted as sequence of tokens, and it can match, not all the time, but at least we have shown that it can match and exceed some of the state-of-the-art convolutional neural network on many tasks. And the effective and efficient transformers model for CN is an open issue. That is, as you mentioned, there are some variation as an efficient transformer called X transformer or X formers. Now, I want to end with two questions for you. And one is, will transformers replace convolutional neural networks in future? And the second question is, can transformers with only fully connected layers, and massive data training achieve satisfactory results? Thank you so much. And these are some of the references I use in this presentation. Thank you.